Hello, mathophiles. In this adventure in algebra, we are going to study subgroups and the definition of subgroup. So we're going to give the definition of subgroup. We're going to prove an equivalent definition, which is the one we actually use, and we will look at several examples of subgroups. So first, let G be a group. Technically, it could be any monoid for this definition. And let S be a subset of G. We say S is closed under multiplication if, for any two elements in S, their product is also in S. So as a first example, the set of natural numbers, it's a subset of the integers, and it's closed under addition. In other words, if you add two natural numbers, you're going to get a natural number. Well, that seems to make sense. Is it true? Well, yes, because the natural numbers are the integers that are non-negative, and if you add two non-negative numbers, you can't get something that's negative. As another example, consider the rational numbers. Every rational number is a subset of is a real number. We remind ourselves, in case you need the reminder, that a number is rational if you can write it as p over q for some p and q integers, and q is non-zero. So we claim that q is actually closed under addition. Well, how do you know that's true? Take x and y in q. Then x is of the form p over q for some p and q. Y is of the form r over s. This is p, q, r, and s, all integers. And of course, we need the denominators to be non-zero. Well, what is x plus y? Well, currently it's just p over q plus r over s. But it's not clear that that's a rational number. It's not clear that that's a fraction. Well, then we go back to elementary school. How do you define addition of fractions? Oh yeah, you do a common denominator. And the simplest formula for a common denominator is to just multiply the first fraction by s and the second fraction by q. And if you do that, you should get sp plus qr as the numerator and qs as the denominator. And since s, p, and q and r are all integers, s times p and q times r are integers, and this sum is also an integer. Similarly, q times s is also an integer, and so you have a ratio of integers. Moreover, since q and s are not zero, q times s is not zero either, and so we do in fact have a fraction. And so that's the point of being closed under multiplication. It says if you take any elements in your subset, the product is also in your subset. Note here, of course, multiplication means addition, which is a bit of a head fake, but one has to get used to that in this course, that sometimes I say the word multiplication, but you have to pay attention to which binary operator we're actually using. Of course, in mathematics, it's also always good to give at least one non-example. So a non-example would be the set of odd integers. So the integers that are odd. We claim this is not closed under addition. So what does it mean to be closed under addition? It means for any pair of odd numbers, their sum is odd. That's what it would mean to be closed under addition. So can you think of a pair of odd numbers whose sum is not odd? Well, the simplest example is 1 and 1. 1 and 1 are both odd numbers, but their sum is 2, which is even. And so we see that we have two elements that are both in O, but their sum is not. So we have a subset of integers that's not closed under addition. So we see the main criterion you have to show is that for any two elements of the set, their sum lands inside the subset. As soon as there is one counterexample, it's not closed. Now we arrive at the definition of subgroup. So let G be a group, let S be a subset of G, and suppose that S is closed under multiplication, which means for any two pair of elements in S, the product is also an element of S. Then S is called a subgroup if it is a group. So of course I have to think carefully and remind myself, what does it mean for it to be a group? Oh yeah, that's right. It has to satisfy three properties. What are those properties again? Oh, that's right. Associativity, a multiplicative identity, and inverses. So for any three elements in this subset, if you multiply those three elements together, you can move the parentheses over and you get the same result. Note here, the distinction is that all the elements are elements of S. Note, because S is closed under multiplication, x times y is in each of these elements on both sides of this equal sign are in fact elements of S. We also need an identity, which means we need an element, let's call it E, that's an element of S, with the feature that for all other elements of S, multiplying by the identity on the left or the right gives you this element G back. So G times E is equal to G. Finally, every element in S is invertible. For all G in S, there exists a G inverse. So it's that G inverse dot G is equal to the identity. So the main point is that you found there's an identity and there are inverses. Of course, one thing you might wonder is that since G is also a group, take your favorite element, little g. It has an inverse in the larger group, and it has an inverse in this smaller subgroup. How are those two inverses related? Similarly, capital G has an identity, and capital S has an identity. How are those identities related? Here's the relationship. The relationship is actually what we call the subgroup criterion. It turns out a set H, so I'm going to use H instead of S because it is customary to use H for subgroup, because apparently H is the letter after G. Yeah, sometimes mathematicians get a little dyslexic. It should be F, but for historical reasons we use H instead, even though we write it on the left. Yeah, we're not always consistent. So a set H is a subgroup if and only if for every pair of elements, x and y in H, x times y is an element of H, and the second part, which is more important, for every x in H, x inverse is in H. So it's worth pointing out this x inverse is the same inverse that you get in G. My point is, since G is a group, there exists an x inverse in G, such that x inverse times x is the identity element in G. And what this is stating is that this same x inverse from the larger group is actually in this subset. So this is sometimes stated as saying you're closed under inversion. So you're a subgroup if and only if you're closed under multiplication and closed under inversion. Please note I am differing from the textbook a little bit. The textbook usually adds another requirement that says the identity element of G is the identity element of H. And you'll see when we do the proof that that fact does pop up in the proofs. However, it turns out that fact also follows from these two conditions. So it turns out in practice, you never actually need to check it. So I've chosen to exclude that condition because it's actually equivalent to this theorem. So as like with the definition of group, I'm choosing something slightly simpler so you have less stuff to check on homework. You only have to check 2 things instead of 3. Admittedly, as far as I'm concerned, I usually take this in my mind to be the definition of subgroup. So it's okay if by the end of the semester that's the definition you remember, because it tends to be the more useful calculation or the more useful definition to use. But it's worth pointing out there is a separate definition and the two are equivalent. And why do I say this one's more useful? Because it gives you 2 properties you can actually check to verify something is a subgroup. As our first example, let's show that the set of natural numbers is not a subgroup of the integers with respect to addition. So according to the subgroup criterion, in order to be a subgroup, you need to be closed under addition, which we already know it is, but you also need to be closed under inversion, which of course in our context means negation. Well, take the number 1. What is its inverse? In Z, it's -1. Last time I checked, -1 is not a natural number, so you're not closed under negatives. The set of natural numbers is not a subgroup. In particular, it is not a group because it doesn't have inverses. As our next example, let's consider this set, B2. It's the set of all matrices in GL2R such that A21 is 0. So that's the entry in the second row, first column. In other words, this matrix is the following form: A, B, 0, C, where A, B, and C are real numbers, and A times C is non-zero. So that ensures that the determinant is non-zero. In general, these are what they call upper triangular matrices, and you could define them for arbitrary n by n, but we're going to stick with 2 by 2 because it makes the argument a little simpler. So I claim that this set Bn is a subgroup of GL2R, but what does that mean? Well, the original definition says that B2 is closed under multiplication and forms a group in its own right, but it's always smarter to use the subgroup criterion. And that's what we're going to do. And so that means we need to check 2 conditions for all pairs of matrices A and B in B2. We need A times B to be in B2. Closure under multiplication. And then the other condition is that for every matrix in B2, the inverse is also in B2, because that's what it means to be closed under inverses. And if these 2 facts are true, then by the subgroup criterion, B2 is a subgroup of GL2R. So that's what we're going to do with our proof. We're going to prove these 2 conditions. And since we have universal quantifiers, to prove condition 1, we're going to let A and B be arbitrary 2 by 2 upper triangular matrices, and then we need to prove that the product is an upper triangular matrix. Now let's start the first part. So let A and B be elements of B2. And what do we want to show? We want to show that the product is also in B2. Note, if you want to do full points, get full credit, you would also include sentences like, we show B2 is closed under multiplication. And down here you would write, we conclude that B2 is closed under multiplication. But more importantly, how do we actually do this calculation? Well, what does it mean for this product to be in B2? Well, what's the definition of B2? Well, it's matrices where this lower left-hand corner is 0. So we need to see that this entry, AB the second row, first column entry of this product is 0. So in other words, what we hope for is to be able to say then the second row, first column entry of this product is equal to 0. So now we just hope for the best. Let's do the calculation. Well, what should we do first? Let's calculate this a dot b comma 2, 1 using the definition of multiplication of matrices. So by definition of matrix multiplication, this is what it should be. We get upper left-hand corner of A times, or no, let me state it correctly. So we're looking at the second row. So we're taking the second row of A times the first column of B. So second row, first entry times first column, first entry. Second row, second entry times first column, second entry. Add the result. Note here, this is our hope. So this is still scratch work right now. We're hoping that we're going to be able to connect the dots. All right, so this is just the definition of matrix multiplication. What other information do we have? Well, we know A and B are in this set, which means their lower left-hand corner entries are both 0, which means A21 is 0 and B21 is 0. In particular, A21 is 0, B21 is 0. It looks like we got 0 times something plus something times 0. Well, 0 times anything is 0. So we have 0 plus 0, which is 0. So we managed to show what we wanted to show, which is that the lower left-hand corner entry in the product is also 0. And therefore, we are closed under multiplication. Of course, in order to finish using the subgroup criterion, we need to check the other condition, which means that given any matrix A, we need to prove its inverse is also in our subset. So let A be a matrix in B2, and we want to conclude that A inverse is also in B2. What does it mean for A inverse to be in B2? Well, it means the lower left-hand entry of A inverse needs to be 0. So that's what we hope to show. Now we just need to fill in the blanks. Well, what is the definition of A inverse? Well, this second row, first column entry is going to involve the determinant, and it's going to be the negative of the corresponding entry from A. Namely, remember from our definition of inverses that this is the formula. You negate the anti-diagonals and you swap the diagonal entries. And then you divide by the determinant. But because A is in this set, this lower entry here is 0. So A sub 2, 1 is actually 0. So we actually get this fact. And 0 divided by anything that's not 0 is 0. And so we get what we wanted to show. So we are closed under multiplication and we are closed under inversion. And again, if you want full credit, you would probably include those sentences. That thus B2 is closed under inversion. So B2 is a subgroup of GL2R, like we claimed, and the proof is complete.